Hi there and welcome to this video for Senior Physics on Quantum Mechanics. In this video we're going to explore the idea of atomic spectra. Now basically we understand that Ernest Rutherford put together a model of the atom which basically had a positive center with electrons running around the outside. But unfortunately a number of these things were found to be flawed. It was basically stated that any charged particle that was accelerating should basically emit energy. Now this doesn't happen because otherwise if it emitted energy the electron would then collapse into the nucleus. And it was up to one of Rutherford's students, Niels Bohr, who actually used the idea of quantum mechanics to solve this problem. Now basically what Niels Bohr stated was that all of the electrons existed in specific fixed energy groups. We call them shell orbitals. Now each of these shell orbitals are specific to a certain element, and the distances between them required the electrons to gain a specific amount of energy. With it being specific, this obviously links to the idea that that energy must be quantized. Now basically what he found was that if we energized any electron, and this can be done either in the discharge tube or using flame tests, as you can see down the bottom, what we are going to do is we're going to energize the electrons to higher orbitals. But because they're in these higher orbitals, they will basically fall back to ground state because they're unstable. Now, as they fall back to ground state, they're basically going to emit that specific amount of energy which was necessary to energize them up to that specific shell. Now, if you can look at the model of the atom on the right hand side of the page here, you can see that we've got our blue electrons spinning around in their shell orbitals. They're all quite happy, but give it a little amount of energy, either by using electricity or putting it in a Bunsen flame. What happens is we're able to energize the electron to higher shell orbitals. Now remember, it's not been ionized, so we haven't generated enough energy to cause ionization to occur, as we saw in the photoelectric effect. What happens is, if it's given a specific amount of energy, it will raise itself to a specific shell orbital. But because it's in there, it's now going to be unstable, so it drops back. And you can see here that it's dropping back 2 shells, and as it does that, it's going to liberate energy of a specific size, a quantized size. This comes off in the form of a photon, and if we have enough of these energies coming together, this is why we get different colored flames which are generated in the flame test, or if we use discharge tubes, different colors which are generated when we electrify them. So basically what Bohr was saying was that we've got quantized energy shells. Electrons can go into those energy shells if they're given enough energy, but because they're unstable, they will drop back to their normal ground state, liberating a specific photon. Now obviously we've got multiple numbers of shells. What this means is we're going to get multiple frequencies of light which are going to be generated of multiple different photon size or quantize. So as a result, they'll combine together to produce a specific color. So basically what this does, if we were then to take that color and then split it using a prism or a diffraction grating, what we'll get is finite lines. Now those finite lines will be specific to a certain quantized amount of light, and as a result we call this a line spectra. Now fundamentally what a line spectra is a fingerprint of what an element's original makeup is made of, and it tells us the number of orbitals and the energy which is necessary for the electrons to go from these orbitals to the next state. So as I said, it basically makes like a fingerprint, and eventually it then drops back to its normal level, which we call ground state. But if it's given enough energy, then the result is the electron will actually leave the shell orbitals, so that there is no link between the nucleus and the electron, and hence it will become ionized. And as you can see in the bullet point there, for hydrogen, that takes 2.17 times 10 to the negative 18 joules of energy in order for a single electron to be ionized in the element of hydrogen, basically to get away from the effect of the nucleus. So what does this all mean? Well, basically we know that energy is quantized in electrons, and as a result they're going to occupy specific shells. So here we've got a diagrammatic version of the hydrogen atom. You can see it's got a positive nucleus at the middle, it's got its single electron, and then we've got all these orbitals sitting outside. Now, the hydrogen atom was explored first. Basically, it was very simple to work with as it only has one electron. Now, as the electron moves to each individual shell orbital, as I stated, it's going to require a certain amount of energy in order for it to get into that orbital. If it hasn't got that energy, it will just remain where it is, remembering that idea that the energy has to be quantized. So, as a result, when it gets to this area, this orbital, it's now going to be unstable, and as a result, it's then going to fall back into ground state. So let's have a look at our electron here. We can actually energize it. So when I energize it and give it a certain amount of energy, you can see it will move into that first excited state. Give it a little more energy and it will go into our blue shell. A bit more energy and it goes back into our red shell, getting further and further away from the nucleus. But remember, that requires a specific amount of energy in order to get there. Now, while it's sitting there, the result is it's going to be unstable, as I stated earlier, and as a result, it will want to fall back to ground state. So what we're now getting, as it falls back to ground state, it will give off these lights. And here are some discharge tubes that you can see showing different colors of light, which are generated by specific amounts of energies being released. If we split these energies or split this light up, we'll be able to see what wavelengths of light make up that light itself. Now, if I give it too much energy, the result is that electron will eventually be ionized, and as a result, it will then leave the atom itself. Now, the first person to do any work on this was Johann Balmer, 1825 to 1898. He was basically a Swiss mathematician, and basically his claim to fame was that he was able to work out and put together a formula which allowed us to work out the energy shells and help Bohr use his idea of quantum mechanics to basically add a theory behind this idea that energy shells basically were quantized. Now, what we've got here is a diagram showing the energy states that we've got for hydrogen. Now, you can see the ground state is down the bottom, and then we've got on the right hand side the different types of shell orbitals, and they're labeled n equals 1, n equals 2, 3, 4, until we eventually reach infinity. On the left hand side, we can see the amount of energy that is required to energize the electron and move it from one shell to the next. Now, you'll notice that it's in the negative, getting gradually smaller as we go higher up on the vertical axis. This is because basically what we're talking about is what's the amount of energy that has to be put into the atom to allow the electron to basically move up to finally be ionized. So ionization is given the value of 0, and as we go subsequently smaller or lower towards the nucleus, the result is we require more energy to actually get it moving. Now, you'll notice that it's in units of electron volts. Now, this just makes the numbers a lot easier to work with. 1 electron volt is given the basically works on 1.6 times 10 to the negative 19 joules of energy. So for every electron volt, we're giving 1.6 times 10 to the negative 19 joules. Now, what you've got to understand is those numbers in joules are far too small. So it makes it a lot easier for us to quantify these small numbers in numbers which are a lot easier to work with. So let's see what happens. So basically, in the first instance, I can move my electron from one shell, and they're going to come out in giving off energy of red wavelength. Then we go to the next shell. We can see that it's going to be giving in the blue. The next shell is going to be giving it in the dark blue, and the next shell we're getting it moving in the purple area. Notice that in each case it is dropping down to its ground state, and it's giving out more and more energy. Now, the higher it's reaching to ionization, the more energy is going to be generated. So that's why you'll see that purple is coming from higher or further away from the nucleus, whereas red, which is low energy, is coming from lower. It takes less energy to get there. And if you use Planck's E equals hf, you can basically work out the frequency and the amount of energy for that type of light. Now, when we look at this with the naked eye, it just comes off as a sort of purpley red color. But if we look at it through a diffraction grating, what we'll then see is that the bands then exist. We can split it up and we get our specific bands. This is what's known as an emission spectrum. Now, Johann Balmer looked at this and was able to do these studies and basically predict and show these bands which were appearing when he split light up. And from this, he was able to come up with an equation. Now, this equation is quite complicated, and it only really works for hydrogen. He was only able to try and justify it. He wasn't, able to justify it. And he used the constant from Johann Rydberg, which is called the Rydberg constant. And he came up with a formula which allowed him to work out the wavelength as an electron was dropping from one energy level to the next. And basically what he had was 1 over lambda, or the wavelength, equals the Rydberg constant, which is 1.1 times 10 to the 7 per meter, times 1 over nf squared. Now, nf squared is your final quantum number, minus 1 over ni squared, which is your initial quantum number. So as you move down from one energy to the next, those are the n values, multiplied by your Rydberg constant, and then do the reciprocal function, and the result is you'll end up with the wavelength. And that will be useful for you when you're looking at a variety of questions that we're going to be looking at later on. Now, as well as Balmer only looked at the visible spectrum, and you can see other spectrums which were actually identified later on. So you can see Balmer there on the second one in from the left, but we also have series called Lyman, Paschen, Brackett and Pfund. And what they did was they looked at, as technology increased, we were able to identify light at different wavelengths, so the ultraviolet spectrum and also in the infrared spectrum. So Pfund was looking up to the ultraviolet, whereas Lyman was looking at the infrared area. From this, we also gathered another equation, En equals negative E1 over n squared, and basically n is the energy level, and E1 is the energy at ground state. So for hydrogen, we've got 21.7 times 10 to the negative 19 joules. And as a result, we can utilize this to basically find out what the energy level is for a specific quantum number. Now, as well as this, once we've produced once we've energized the electron and allowed it to fall back, we'll get colors which are produced, which we call our emission spectrum. But also we can use something where we're shining light, and what happens is it will absorb the light, and we get an absorption spectrum. Now, an absorption spectrum is where you've got all the colors of the rainbow, and the light has actually been absorbed. In this case, what we're doing is we're losing the light, and this would happen when you energize those electrons. It takes that energy and moves it out. So as a result, you'll get a black line on a color background, or if you've got an emission spectrum where it's dropping back, you've got a black background and you've got your colors coming off. The key thing to understand is that the bands will always be in the same position because they're all coming out with the same amount of energies with the same frequency. So if you look at the diagram that we've got here, we've got a hydrogen spectrum where we've got an emission spectrum which is generated on the top. You see your black background, and what's happening is it's dropping back to its normal ground state, and as a result that's giving off light of a specific frequency. And then we've got absorption spectrum below, and you can see the black lines which are generated in our colored spectrum because it's taking in that energy. what you'll notice is both of the patterns, both of the bands are produced in exactly the same space. Okay, so well, I hope you found that useful with respect to looking at atomic spectra. I've put up a load of worksheets for you to work through. Also check out my video on PhET. PhET does a nice simulation which will show you how those emission spectrums are produced. Do also check out any of our worksheets and resources on aussiephysics.com, and yes, by all means subscribe to that, and you can use any of those materials free of charge. Well, I hope you found this useful. Thanks for watching, and I look forward to you joining me again. Bye for now.